energy. What does it all mean? Today, in this video, we will be going over all of this and taking you through 2 labs to help understand it. So thank you for joining us. Thank you.
Today we will be going over energy, work, power, kinetic energy, and the work energy theorem. Their definitions and their units, and how we can apply them to real life. This is the thumbnail for the video.
In classical physics, energy is the capacity to do work. What is work, you ask? Work occurs when a force exerted on an object moves that object parallel to the direction of that force. When work is completed over a power... Dang, I said completed! I hate my life. When work is completed over a period of time, it results in... What are you doing? When work is completed over a period of time, it results in a power output. Have you never signed a sign of ship before?
No, I haven't actually. Okay, one more. Next, we're gonna do a lab that demonstrates work and power output.
First try!
Let's head to the bleachers.
That bar right there is good.
Probably good.
Higher! You need to be in that... Hey girl.
Jackson versus Jackson.
Ready, set, go. Stop. Ready, set, go. Ready, set, go. No, stop. That's too slow. Go back. Get. I have to restart. Ready, set, go.
In this experiment, our system was Earth and Jackson. A system is a group of 2 or more objects. Stop it! To clarify, a system is the part of the universe that you choose to analyze. So in this case, our system was Jackson and Earth. There you go.
Now let's go to the poster board to do some explanations on this lab.
So, we defined work already, but what are the equations for work? What are the units of work?
We have 2 equations for work. The first equation is work equals the force times the distance times cosine of theta.
So the cosine of theta just means that we're only looking at the force parallel to the direction of its displacement.
Imagine you have an object sitting on a flat surface and there's a force being applied at an angle. You only pay attention to the force being applied parallel to the displacement. So that means when you break the force into its components, let's say this is your angle right here, you only pay attention to the cosine, this component right here, because that's what's parallel to the displacement. This is also the reason why if your force is parallel to this object, you can ignore the cosine theta, because cosine of 0 degrees equals 1. So what are the units of work? If you think about it, what are the units of force? The units of force is a Newton. What is the units for distance? That's a meter. And the ratio of cosine theta is unitless, doesn't have a unit. So we end up with this unit here, nu meter, which we call a joule, which we represent with a capital J.
In this lab, we're focusing on power output. So what is power and how does it relate to work?
Power, signified by P, equals the amount of work done divided by the change in time. Knowing that work has a unit of joules and time is measured in seconds, what do you think the units of power is? Knowing that work is defined in joules and change in time is in seconds, we know that the units for power is joules over second. But in physics, we have a special word for this, a special name, and this is called watts, signified by capital W.
Sunset, the sundress, you can tell by your face. That's a song, you putzes. This is not going in the video.
Here we have organized into a table all of the data we took from our bleacher lab. For both Jacksons, we have their mass in kilograms. We used Fg equals mg to convert it to weight in newtons. We measured their time during the lab, and we measure the height of the bleachers. And we're not going to get into this right now, but you just need to know that we're only focusing on the vertical displacement. In addition, when solving for work, we're ignoring the cosine theta, because technically what's moving you up the bleachers is your normal force, which is parallel to your vertical displacement. So with all of this data, pause the video and try and solve for work on your own, and then check your answer. Wait, I don't know if this is allowed in a video. I need a sip of water after that one. Stop. Stop. Okay, so these are the answers you should have gotten for your work. For the first Jackson, we use 4-line format. So we identify our data, our force, we don't know what our work is. Our force is that 774.2 newtons that we measured from over here, and the distance is the 8.2 meters. And because we're ignoring that cosine theta, all you do is force times the distance, which gives you 6,348.4 joules. For this Jackson, it's the same thing, except for instead of the 774.2 newtons, he measured at 695.8 newtons. So when you plug that in, you get 5,705.6 joules. So now that we have the work for both of them, try and calculate the power for each Jackson. For our first Jackson, we got 991.9 watts. Over here, we got 967.1 watts. So looking at these answers, you guys notice anything different? Or anything unique? Oh! Now bring it back. Have some physics to do. Alright, just start recording. I'm about a monologue.
Go.
So, hopefully, after solving, you come to the same answers we did. Again, we used 4-line format. We came to, for the first Jackson, we got 991.9 watts. For Jackson number 2, we got 967.1 watts. Do you guys notice anything unusual about this data? Our Jackson over here, he ran it in a slower amount of time, yet he still came out with more power. This is because his ratio from work to time was higher. So even though he ran it in a shorter amount of time, a longer amount of time, his power came out to greater than this Jackson who ran it faster. Did I stutter too much?
No.
Did I stutter? Did I stutter? Now on to the next lab. To the pole vault runway. In order to set up a video that you can analyze from on your program, you have to have some sort of reference. So for us, for this
Oh no, get a picture! Get a picture! Make it...
俺はおちんちんの大好きなんだよ。We've already talked about energy. Kinetic energy specifically is energy relating to motion. Kinetic energy is what was demonstrated in this lab. Jack's running. Kinetic energy is the energy. And for the third National Chair Olympics, throw it. Discus. Discus. Please try not to kill us.
No, yeah, the other direction.
Oh!
Now let's head back and analyze Jackson's work.
You're supposed to just stare. It was just supposed to get more awkward and awkward.
Listen, I get night sassies. You better shut up and get to work. Okay, no, that's not. If it ever comes to naturally, have your camera rolling. Stop. Go. Keep it together.
From Logger Pro, we have calculated the initial velocity to be 1. Okay, wait. Dude, I can't.
No, I'm still rolling. You go.
I can't read and write at the
No,
same time.
there is no script.
We have calculated the initial velocity to be 1.07 meters per second.
From Locker Pro, you forgot to say. It
already
was from
said-
Locker.
I already
Okay,
said
sorry. Keep going.
And the final velocity to be 8.67 meters per second. And also, we have previously measured my mass to be 79 kilograms.
Your weight is big.
And we are solving for work.
Ding.
No, here you go. Alright, the equation we're going to be using is work equals change in kinetic energy. But this is equivalent to... This equation is the same as this one. If we write kinetic energy final minus kinetic energy initial. Now, we rewrite this as work equals 1/2 mass of our final velocity squared minus 1/2 mass of our initial velocity squared. For reference, kinetic energy is equal to 1/2 mv squared. Now, using this formula, try and find the work I used to speed up. Hopefully your work looks something like this, and you came out with 2,924 joules. This means that from 1.07 meters per second to 8.67 meters per second, I expended that amount of work. Now that's a lot of work. This equation and formula is known as the work energy theorem.
What's the definition of kinetic energy?
The energy of gravity.
Wrong. What is our system for this lab?
It's just Jackson, right?
Wrong! So, what did we learn today? We defined work, power, kinetic energy, and systems.
We went over the equations and units for work, power, and the work energy theorem. And we also worked through the 2 labs to help deepen our understanding of this concept.
Thanks for watching Sub to
Assume spherical answer.
Assume spherical
answer. Nice.
We still need to define the system and kinetic energy.
So, we defined work already, but what are the equations for work? What are the units of work?
We have 2 equations for work. Our first equation is work
See, that's good.
equals the force
No one ever told me
times distance times cosine of theta.
Does you see cosine of theta?
You're fixed for 2 weeks.
Dude.
What? No. Are you serious? No, these were ones we got today, right?
No, it may have expired 2 months ago.
No.
03/21.
Wait, it's no, it's not.
Wait, no, that's not
Wait, it says
right.
2022?
Yeah, it says 2022.
Oh, I saw the 03/12 and I was like,
Hey, I want to hear my voice more.
we're only looking at the force parallel to the direction of its displacement.
Imagine you had an object.
That's good.